Hi everybody. So we are in our first lesson about limits. In the last class, we established that the instantaneous rate of change of a function is equal to the limit of the average rate of change, right? We talked about this in the last class. Is you keep on doing the average rate of change, right? Which is the difference quotient over shorter and shorter time intervals, or bringing the 2 points uh, over which you're doing the average closer and closer together. And when you do that, then you get the instantaneous rate of change, right? So now we need to study limits because we have realized that the limit is going to be an important concept in calculus. So what is a limit? First of all, let's be clear about how to read this equation here. That is going to be read as the limit of f of x, right? So that's this piece of it, the limit of f of x as x approaches 1, that's this piece here, is equal to 2, right? Right. So remember that the limit is a y value, and the x approaches 1 is the x values. So x approaches 1 means x gets closer and closer to 1. Okay. So now let's take a specific function. F of x is equal to x squared minus 1 over x minus 1. The first thing you're going to notice is that you can factor the top, the difference of two squares, and you can cancel a common factor on the top and the bottom. And this gives us the insight that this function f of x has a hole at x is equal to 1. X is equal to 1 is going to be an excluded value, right, for the function, because you can already see if you put in x is equal to 1 in here into the original function, you are not able to do that. You get 0 over 0. So that's an excluded value. Okay, so let's take a look at it graphically. If you plotted this function, if you just put this equation into Desmos, it's going to give you a graph like this, which is what we would expect because we see the line here, x plus 1, right? This is the line, except that we have taken out just 1 point out of that line, and that is the hole at x is equal to 1. Okay, so graphically, when we talk about a limit, this right here is just the function. The line and the hole, that's just the function. What does it mean when we say the limit of f of x as x approaches 1? Well, that means that we're looking here, and you got to think of two things happening. The first thing is that the x values are getting closer and closer and closer and closer to 1 from both sides, right? That's what's happening with the x values. The limit is going to be equal to what happens to the y values. As the x values get closer and closer to 1, we're trying to see, is there a y value that we get closer and closer to? And you can clearly see that that y value that we get closer and closer to is 2, right? So we can conclude from this that the limit of f of x as x approaches 1 for this particular f of x, that y value that we get closer and closer to as x gets closer and closer to 1, that's equal to 2. Okay, so graphically, that's what's happening. Let's think numerically. Numerically means we're actually literally putting in x values into the function. Here's the function. And we're putting in x values, and we're making those x values closer and closer and closer to 1. We already know that we cannot put in 1 into this function because then we get a 0 in the denominator. So we can't do that, but let's put in numbers that are close to 1. So here I have 0.8, 0.85, 0.9, and so on, all the way to 0.99, right? So that means on the left side in this column here, here's 1, right? And I'm approaching 1 in these numbers here from the left of 1, right? So really, we could even say this is our approaching from the left side. You know, x is approaching 1 from the left side. Now, I stopped at 0.999, but of course, you know that I can go on, right? I could say 0.9999, 4 nines, or 5 nines, or 6 nines, or 100 nines, or 1,000 nines, and I could go on forever, right? And that's why we have this notation, x is approaching 1, and it can go on doing that. Well, let's take a look at what's happening to y. Well, it's pretty clear, right? Y seems to get to 1.98, 1.99, 1.999. And if you go on doing this, you're going to see that Y just goes on getting closer and closer to 2 from the left side, right? From the left side, meaning from these values that are less than 1. Okay, let's take a look at what happens from the right side of 1, right? So from the right side of 1 means x is approaching from values that are greater than 1. That's what the plus means there, right? So here we have 1, and then the numbers are coming from numbers greater than 1. So 1.2, 1.15, 1.1, and so on until we get to 1.001. And of course, we could go to 1.0001 and 1.00001 and so on. And you can clearly see that the trend for the y values is again 2. The limit is not 2.001, right? So make sure you don't say that. The limit means what number are we getting closer and closer and closer to. And that number for the y's would be 2. So that's how we look at this from a table or numerically. Analytically, means looking at it with algebra, right? So you know this is what you did in pre-calc. So we would look at this limit like this. We'd say, well, what happens when I put in, oops, I have a typo here. That should be x minus 1 on the denominator. If I put in direct substitution, try to put that arrow number in, I'm going to get 0 over 0, which means I need to do some algebra. And that algebra will be factoring and canceling a common factor, and then putting the arrow number in again, and you can see that the answer is 2. So we come to the same answer analytically, right? And in words, the limit of f of x as x approaches 1 is equal to 2 means that as x gets, we say arbitrarily, and I'll explain that word in a minute, arbitrarily close to 1, as x gets arbitrarily close to the arrow number or 1, the function f of x gets arbitrarily close, that's a long word, close to 2, right? And arbitrarily just simply means as close as you want, as close as your little heart desires, right? So you can make y as close as you want to 2 by making x as close as you want to 1. That's what we mean in words by the limit. Okay, next thing is a little critical thinking exercise. So you may want to pause the video right here and try to sketch a function where the limit of f of x as x approaches 1 is 5, but f of 1 is actually 3. So go ahead and pause the video, see if you can sketch a graph that looks like that satisfies those conditions. And hopefully you drew something. I mean, there's a lot of different answers that you could draw, but hopefully drew something like this. Here you have x is equal to 1. Here I have y is equal to 5, and then I have y is equal to 3. You could draw a line, right? But you don't have to draw a line. It could be something like this. You know, here's a function. As x approaches 1, y is getting closer and closer to 5. But at x is equal to 1, the function value is actually 3. Okay, so that's a little critical thinking problem that summarizes some of the concepts above. Okay, let's move on to limits from tables. Okay, so limits from tables, we'll do a couple examples and then we'll summarize. Based on the information in the table at the right, what is a reasonable guess for the limit of f of x as x approaches 2, right? So be very clear in these limit problems, the arrow number is 2, right? So on the table, the x values should be approaching 2. So let's make sure they do that. Okay, let's see, 1, 1.5, 1.8, 1.9. Yeah, it looks like it's approaching 2 there. So this is approaching 2 from the left, or from numbers smaller than 2. And then this right here is approaching 2 from the right, or from numbers greater than 2. Yeah, all that looks good. So we can use this table to get an answer to this problem. So let's look at what's y doing. Looks like we're approaching 3.997. Now remember, that's not going to be my answer because I know that I could make the x closer to 2, and it seems like a reasonable thought that the y would do something like getting closer to 4, right? So the limit from the left side looks like 4, and when I look at the right side, same thing, right? It's 4.003 here. If you go ahead and get closer, it's probably going to do something like 4.001 maybe, right? So getting closer to 4. So I would say that a reasonable estimate for this is 4. Okay, can you be sure that your estimate above is really the limit? Why or why not? Provide a sketch if possible to explain your reasoning. So here the answer is actually going to be no. We can never be sure from a table. A table is always an estimate, right? Because unlike a graph, which actually shows you what is happening to the function as you get even closer, here I didn't really know what happens if I were to get even closer to 2, right? You know, there could be some weird situation like this where I'm just going to zoom in, right? So say I'm at 1.99, which the table has, right? And I know that my y is up here at, this is 3.997001, right? And then on the other side, I know that at 2.001, my y is at 4.003001, right? So this, say 4 is right around here, say 4 is right around here, right? And I know I'm getting closer to 4, right? It seems to be getting closer to 4 on both sides, but who knows? All of a sudden at 1.99995, maybe my y's drop down here and do something different altogether, right? I just don't know from the table, right? Or maybe as I get to 2.0005, right, closer to, this should have been 2, I'm sorry, closer to 2 on the other side, maybe the y values jump down to 0 and do something down here. The point is, from a table, you cannot be sure. Okay, so next question gets us to which table would provide the best estimate for this problem, a limit of f of x as x approaches 1. So I'll say in looking at a table, you want to look for 3 things. Number 1, that the arrow number x, that x actually approaches the arrow number. Okay, if x is not approaching the arrow number, then the table is useless in terms of a limit. So we want to check that. 2, we want to check is that we are approaching from both sides. If you're not approaching from both sides, then you cannot make overall limit statement. So if the table doesn't show you that, then you're out of luck in estimating a table limit. What else? The third thing is that you want to be getting closer and closer in terms of like a zoom effect, right? In other words, the number of decimals on either side should be increasing. Let's put it this way, number of decimals on either side of arrow number should increase. And so let's see if that is happening in these tables, or in which table is it happening the best. So if I look, first of all, my arrow number is 1. So am I approaching 1? Well, definitely in this table, I'm approaching 1. In this table right here, I'm also approaching 1, right? From both sides here, it looks like. So this one's okay. This one is approaching, looks like 0, right? So it's not approaching 1. So I can just eliminate that one. This one is approaching 1 also, right? So the approach, you got to look at all the numbers in the table. In these 2 tables, the 1 is in the middle. In this table, the 1 is on the end, but we are getting close to 1 in all 3 of those tables. Okay, so that was our first condition. Approaching from both sides. Well, in B, we're not approaching from both sides. We're just approaching from the left side. So that one's out. Okay, for an overall limit, that one's out. Closer and closer zoom effect. Well, let's take a look here. It goes 0.5, 0.9, and then 1. So not really zooming in. Here, it does better. 0.9, 0.99, 0.999. And on the other side, 1.1, 1.01, 1.01. So yeah, I would say this would be the best one. C would be the best table to estimate a limit from. Number 4, the table below gives values of a function at selected values of x. Which of the following conclusions is supported by the table? So once again, be really clear which one is x and which one is y. So take a look at what x is doing. X is here. It is approaching 4, right? Approaching 4. And then on this side, it's approaching 4 as well. So we're approaching 4 from the right and the left. So the arrow number is 4, right? So let's make sure that we only consider those. This one's out, right? Because the arrow number is not 6. Okay, now let's take a look at the y values. The y values look like from this side, right? So if I look at these y values, then from this side, they are approaching 6, right? However, from the other side, they don't seem to really be approaching anything. They're doing all kinds of things, right? So the left side approach looks like I cannot conclude that I'm approaching 6 from the left. So that's out. If I cannot conclude 6 from both sides, then, I certainly can't say an overall limit is 6. So I'm left with just this conclusion, C, which is that from one side, from the right side, I seem to be approaching 6. Okay, so that's kind of a summary of what we need to know about tables. And now let's move on to graphs. Okay, so this is a type of problem you've definitely done in pre-calc and in the summer packet. So please just pause the video for a minute, and then you can unpause it and check your answers. Okay, so you can go ahead and check your answers. Basically, your takeaways from here are be able to identify a function value at a certain point and keep that straight in your mind from the limit value, right? Because we look here at -1, for example, you can see that the limit as x approaches -1 from both the left, let me get a different color here, from both the left and the right, and overall the limit at -1 is 2. However, the function at -1 is at 4. So that's an important concept. You want to make sure you understand the left and the right, the one-sided limits, right? So in right here at x is equal to 2, approaching from the right is written like this, right? And that means from values that are greater than 2, right? X is coming in from the right. This means from the right, okay? And you can see that that answer is 1 because the y values are approaching 1, okay? But if you're approaching from the left, right, the 2 minus, that means from the left. So we're approaching from this side, the y values there are approaching -1, right? So in other words, you want to be clear on your one-sided limits. And also things like here where the function ends, if you talk about approaching -4 from the left, right, or from the minus side, you cannot make a statement about that. That part is not in the domain of this function as shown. So you're going to say D&E for a question like that. Does not exist, okay? Or sometimes you might say not enough information, but I think D&E works most of the time. Okay, so now that we have looked at limits of functions in all the different ways, graphical, numerical, analytical, and words, let's do a problem where we connect these multiple representations of limits, right? Graphical, numerical, analytical, and words. So here's a problem where it says, let G be a function that is decreasing for x is less than 0 and decreasing for x is greater than 0. If that means the y values are going down, right, as you move right. If the limit of G as x approaches 0 is 3, which of the following could represent the function G? Okay, so we've got a few conditions, and we want to make sure that we choose only those equation. The first one is an equation, the second one is a table, the third one is a graph, and they're saying choose the ones that satisfy these conditions that we've been given here, the conditions that we're decreasing and that the limit as x approaches 0 is 3. So let's start with the graph. That's the easiest one probably. Clearly, as for x is less than 0, right, which is this side, x is less than 0, as x moves right, in math, when we talk about increasing and decreasing, you're always moving right. X is always moving right, and then you're looking at what y is doing. So clearly, as x moves right, y is decreasing, and again, at past 0 value, when x is greater than 0, also y is decreasing as x moves right. So this definitely passes the decreasing condition. Let's take a look at the limit condition. Is the limit of this function as x approaches 0 from both sides? Yep, it sure looks like the limit is 3. So that function satisfies both of the conditions. Okay, let's take a look at the table. In the table, we are approaching 0, right, from both sides. So that's good, and it looks like, well, I don't know. It looks like the limit is all. It does. I don't think there's evidence, right, that the limit is 3, because the function value here, g of 0, is 3. But as we approach 0, these numbers are anything but 3, right? It looks more like we're not even sure what's going on there, right? So I would definitely say this table doesn't satisfy the conditions. Let's take a look at the equation. The equation, g of x is equal to that. This is a piecewise function, right? So g of x is equal to this for x not equal to 0, and it's equal to 5 for x is equal to 0, right? So we can say g of 0 is equal to 5, right? That we know. Let's take a look at this limit from an algebra standpoint, right? So remember, this equation is the 5 part of it is only at x is equal to 0. But the limit doesn't care what happens at the arrow number, it just cares about the approach. So the only equation we need to use in the limit is the other equation here, right? The negative x squared minus 3x over x. So let's take a look at that. So if I just think about this, negative x squared minus, oh, they were sneaky here. Careful about this negative sign. This negative sign is out front of the fraction, okay? And so we have this and then this. So let's see. Well, I cannot put 0 in because I get 0 over 0. Let's factor out an x on top, right? And see what happens. Now I can cancel the two x's, and now I can put 0 in, and the limit is equal to 3 because this negative multiplies with that negative, and I get 3. Okay, let's talk about the increasing, decreasing, and how we analyze that, right? Because we don't know. This function in number 1, we just showed that it has a limit as x goes to 0 of 3, but does it actually decrease for x less than 0 and x greater than 0? You'd have to know, it's your pre-calc skills here. You want to know how to plot this function or sketch this function, right? So I'm just going to write it here again, and then we'll take a look at this function and see if we can make a quick sketch. So the first thing is to realize that when x is equal to 0, this function is at 5, right? So we can put that point in. And then we just factored, right, and showed what happens when x is not equal to 0. Let me do it again here so that in case you missed it, you see it again. These factors cancel, and I get negative x plus 3, right, if I distribute that negative sign. Negative x plus 3 is the equation of a line. So I know that when x is not equal to 0, this function is just a line of intercept 3 and slope negative 1. So that means the intercept is going to be here, but we know that the actual value will not be included, right? Because I have to be just for x not equal to 0. And then the slope is negative 1, so it's going to look something like this, right? So that's what that function is going to look like, and it is decreasing then. So it's decreasing when x is less than 0, and it's also decreasing when x is greater than 0. So that means that number 1 works as well. So 1 and 3 could represent a function which is decreasing for the left of 0 and right of 0. That means for all values, by the way. And that's another problem, by the way, with the table, right? Because the table, it looks like, we're decreasing here and we're decreasing here, but who knows what happens past these numbers at the ends of the table, right? So anyway, so that connects all our different representations of functions and how to talk about the limits with that. Okay, so I think we're pretty much done. Let's do some takeaways. The limit, so pause the video and try to do it yourself before you listen to what I have to say. Takeaways are the limit of f of x as x approaches -1 is equal to 2 means that for the graph of f of x, as x gets closer and closer to -1, right? So here you want the arrow number. As x gets closer and closer to -1, y gets closer and closer to 2, right? So that's what that means. Okay. The limit of f of x as x approaches 4 from the right is equal to 0 means that as x gets closer and closer to 4 from the right side of 4, right, y gets closer and closer to 0. If the limit of f of x as x approaches 0 from the right is equal to 0, and the limit of f of x as x approaches 0 from the left is equal to 1, then the overall limit of f of x as x approaches 0 does not exist, right? This is a jump in the function, and it's going to mean that the overall limit doesn't exist. True or false? If f of a is equal to d and e, then it must be that the limit of f of x as x approaches a is a d and e, and this is false, right? And I could simply draw for you a graph that looks like this. And there you go. There's a function with a hole at at x equals a, but the limit, so this function right here, f of a equals d and e, but the limit, I'm just going to make up a number, the limit of f of x as x approaches a is 5, right? So just because the function doesn't exist at a particular value, it doesn't mean that the limit doesn't exist at that particular x value. Okay, and then we said that when we're looking for a limit from a table of values, you want to be clear which column or row is x and which is y. You want to identify the arrow number and make sure that the x values are approaching this number. Then you look at the y values and you look at what they are doing in order to estimate your limit. A limit from a table is always an estimate. And the three conditions for the estimate to be a good one are that x approaches the arrow number, that x approaches from both sides, and then the last condition is that the decimals are getting more and more. You're zooming in as you try to make your estimate. Alrighty, well, I hope you enjoyed that, and we'll talk to you soon.